carbon has several different crystal structures that it can crystallize in. It's what we call an allotroph, right? Meaning it's a single element that can have different crystal structures. The word polymorph is more common, but that technically refers to compounds like zinc sulfide that can exist in two different crystal structures. If it's a single element that can exist in several different structures, we call it an allotrope. But it's basically the same thing. So the structure that you might be familiar with is diamond and graphite, right? Those are the two common ones for carbon. Let's start with diamond. What does the structure look like? Well, here's the structure. You've seen it before, right? You've seen something similar to it before. What does this look like? Hopefully you've realized that this looks a lot like zinc blende. What was the only difference? In zinc blende, these atoms filling the interstitial sites inside the unit cell, those four right there, they were a different atom than those occupying the corners. But in the case of diamond, it's all just carbon. We know that carbon wants to form 4 bonds, right? Every carbon wants to form 4 other bonds. So in the case of diamond, it just kept on finding other carbons nearby, and it kept on forming single bonds to other carbons in the vicinity. The way that you can do this is with this diamond cubic lattice. So it's not zinc blende. Zinc blende would have 2 different atoms. It's diamond cubic. And another important structure that forms in this is silicon. Silicon, pure silicon, also forms in this crystal structure. Now, since we know that it's close to zinc blende, we also know that it also resembles an FCC lattice. It can be thought of as 2 interpenetrating FCC lattices. Again, here's one of those lattices. We see it, the normal one. There's the face and the atoms on the corners. But there would be another one if you were to start with this atom. This atom, you could do another interpenetrating FCC lattice just like we did the zinc blende. Another common thing that you might be familiar with carbon is the graphite crystal structure. You might know that these exist in layers. You have layers of graphite that can easily slide past one another because they're not strongly bonded one with another. They're weakly bonded. So you get these layers of graphite which are very strongly bonded in the layers. They're quite strong. But the forces between these layers are just van der Waals forces, and so they're very weak. So the pencil that you've probably got nearby, the reason why you can write this and it leaves behind a layer of gray, graphite behind it, is because they're so weakly bonded. They slide past one another quite easy. It wouldn't work. A diamond pencil wouldn't work well because you're not going to scrape off a layer of diamond. And it's not gray anyways. It's transparent, right? So didn't we just say that carbon needs 4 bonds? Well, let's do a count here. How many are they each bonded to? Here's one carbon. I count 1, 2, 3 bonds. So that's not right. What's going on here? What's going on is that you have some of these are double bonds, right? So if you look at it, if this is a double bond, well, let's say that's a double bond, single bond, then you get a double bond, single, double bond, single. You have an alternating double bond. So every other one of these bonds, right, this one, that one, and this one would be double bonds, and those are alternating. We call this a resonance structure where the bonds are flipping back and forth. It could just as easily be, if I do it in a different color, it could be this one, that one, and that one, right? And so it alternates between those. That's called a resonance structure. But it shares double bonds, and that's how it gets, on average, 4 bonds, okay? You can also get really exotic allotrophs of carbon, things like buckyballs, right? This is an example of a buckyball. This one's shown here. This is a C60. There are 60 carbons that make up this structure, right? Now, is this a crystal structure like the one we defined in the past? Is it periodic and long-range order that could fill all space? No. This is an individual molecule, right? So it can't you couldn't wallpaper a wall with it. If you took these buckyballs themselves, you could form an FCC lattice, and people have shown that you can do that, which is pretty slick. But the buckyball itself is made up of 60 carbon atoms. If you look at this, there are 12 pentagons, 20 hexagons, and it was named after the guy Buckminster Fullerene, the same guy who invented the geodesic dome, which you've seen if you've driven down to southern Utah and seen those funky sort of buildings that look like geodesic domes, half domes sort of look a bit like that. And then, so these don't have a ton of applications, I would say. They're an interesting novelty, but it's not like they're changing industry in major ways that I know of. Prove me wrong. But there are things that are really important, and these are carbon nanotubes. Carbon nanotubes are really important. They're made by essentially rolling up a sheet of graphite, right? If you come back here to our graphite, right, what would happen if you took this end over here and you rolled it up and you connected it to that end. You bonded it to that end. All of a sudden, you would have a carbon nanotube. These can be single-walled or multiple-walled, right? You can have a single tube that forms, right, where this tube exists. Or you could have multiple tubes, right, that are sort of cylindrically concentric with one another, okay? That's also possible. These are pretty cool. Tube diameters are typically 100 nanometers or less is what we typically end up with when we make these. The length of the tube is something like 1,000 times longer than the diameter. We already said that there's multiple walled carbon nanotubes as well as single walled. You can end up with really strong, stiff, ductile materials with tensile strength like 50 to 20 gigapascals. That's crazy. That's a huge tensile strength, way bigger than anything else that's known. This is an order of magnitude more than carbon fibers. So when you see carbon fibers like composite layups into carbon fibers, this is still 10 times stronger than those even in tensile loading. So pretty exciting properties. They're pretty amazing. What's the problem? How do you make them into anything that's very long? How do you make a continuous strand that's 10 feet long, 100 feet long? How do you make ropes out of this, out of that? We don't know how to do that yet. We can make them, like I said, something like 1,000 times longer than the diameter, so 100 nanometers times 1,000, but that's not necessarily super duper long. So what you typically end up with is chopped fiber reinforcement, right? If you've got a composite, you can lay it up with continuous fibers. These things be things like carbon fiber, or you could make it up with a bunch of discontinuous carbon nanotubes running through it. And so that still has some advantages. A lot of sports equipment, for example, really high-end sports equipment is carbon fiber reinforced, and then there's others that are carbon nanotube reinforced. And there looks to be some advantages in using carbon nanotubes. These things have remarkably low density, less than 2 grams per cc, and given the strength they have, the specific strength, the specific stiffness, that means the mechanical value divided by the density, puts it in a really amazing spot. So these would be sort of a perfect fiber for composites. What's really cool is that depending on where you connect these things, depending on whether you connect it like we showed it here, or whether you connect it to connect to that one, or if you connect it to that one, you can make these things line up differently. You can skew it. You end up with different electronic properties. They can be, as far as I know, you can have insulating, conducting, and now even semiconducting ones. So from an electrical or a design perspective for functional materials, these are really interesting. There's been lots and lots of work in the whole field of nanomaterials, carbon nanotubes. It's hard to overstate the impact that they've had on that field, and there's been lots of research on them. One thing that gets thrown around a lot is this idea of a space elevator, where if you wanted to, instead of shooting rockets out to outer space, which we all love to watch SpaceX and company do these sort of things, it's still a high energy proposition. How much cooler would it be to put a counterweight out in space that is in geosynchronous orbit with the Earth, meaning it stays directly over some spot? So you anchor it, say at the equator, you've got this rope or cable that goes out into space. You could just climb right up it and get out to space, and you could escape gravity that way. The problem is any known material, if you use the best known materials we've got now, braided steel, nylon rope, whatever it is, all of those would break under its own weight based off of how long this was, except for carbon nanotubes, if we could only make them, several miles long, which we don't know how to do yet. Maybe that will happen in the future. For now, I think it remains an interesting imagination concept for engineers to think about. Okay, the key things to take away from this one is, again, polymorphism is when you can have multiple structures existing for a compound, and we call that allotrophy when it's for a single element. Okay, so that is the structures of carbon.